Hello everyone. There's been a lot of debate and controversy over the use of carbon fiber rods in metal detectors, and I thought I would do a little video and demonstrate what some of those issues might be and what some of them really aren't. To do that, we'll start off with a Minelab Equinox, and for this, we're going to run through some different frequencies and modes, and I've opened up the discrimination mask all the way to 0, and that's because the carbon fiber rods tend to be very low conductors. In fact, they are almost exactly the same as salt water, and I'll show you that in the beach mode in a minute. But so for the carbon fiber rod, I'm using one from a Fisher prototype. It's one you've not seen before, but it does the same thing as all the others. I just happen to have it laying around. So let's start off with the Equinox at 4 kilohertz. And at 4 kilohertz, we get a decently strong signal, probably about 6 inches. And I've measured all this before, so I'm not going to hold rulers and yardsticks up and stuff. At 10 kilohertz, it's around 8 inches. And at 20 kilohertz, about 10 inches. And at 40 kilohertz, about 12 inches. These are single frequency modes. Multi-frequency, the typical part multi-frequency mode has a 39 kilohertz component to it, so you're going to get it pretty deep in multi-frequency as well. But obviously we don't use a carbon fiber rod like this. We don't wave it across the coil. It's affixed to the coil. But let's go back to 4 kilohertz. And the way it's affixed to the coil is on a pivot that is not perfectly rigid, and so it's going to move around. It's, as you bang the coil on the ground, it's going to flex and give, and you may want to angle it back for certain conditions. And you can see at 4 kilohertz, we're not really hearing this. It's fairly insensitive to movement pivoted at the coil. Now, not like this, but like this is fine. That's at 4 kilohertz. Let's go to 40 and do the same thing. Okay, quite a bit more sensitive. Doesn't take much. And so this can potentially cause you what seems to be ground noise, but it's really motion impact noise. And it may take a bit of an impact. In a normal swing, you're probably not moving this thing much at all. But when you bump up against stuff, you can get quite a bit of movement. And so obviously this thing is frequency sensitive, both for normal detection like this, and also for real use. The high frequencies are going to be far more sensitive to minor motions like that. So let's take this thing now to beach mode. And remember, I said this thing looks like salt water. And in beach mode, salt water gets notched out. And so in beach mode, you don't hear it. Again, it looks just like salt water. Now, let's go to prospecting mode. Now, prospecting mode is a dominant 40 kilohertz mode, but it is a multi-frequency mode. There's a 40 kilohertz component, and there's a 5 kilohertz component, I believe. And it also runs with different filters. So this is probably a first derivative type detection. And you can see this thing, my goodness, it's probably 16 inches, it's still getting it. And so in prospecting mode, it's even more sensitive to slight motion than it is in single frequency 40 kilohertz mode. Yeah, it doesn't take much. So this could be a real issue for VLF prospecting detectors, or when using a multi-mode detector for prospecting. This could be a big problem. Let's see. Does it affect depth? So let's go, well, we'll just leave it here. So in prospecting mode, I've got a number 2 lead shot, and it's picking it up, 4 inches or so. Not any problem. And again, we don't normally do this, but let's just lay that there. And still getting this thing at 4 inches. It doesn't have any effect on depth. What it does, it does upset the null of the coil. And so if you upset the null of the coil enough, you can put the detector into overload mode. You've got too big of a signal for the electronics to deal with. But even laying the thing completely across the coil does not seem to cause an overload condition. You're not hearing an overload tone, and it's still detecting the number 2 shot just fine. And so I would expect that carbon fiber rods don't present a big enough signal to cause an overload issue, or really any kind of real detectability issue. Whether it's sensitivity or whether it's VDI or whatever, or depth readout. They're probably all going to be about correct, no matter what lower rod you have, no matter what frequency, and so forth. So one more thing though to show you, and for this I'm going to switch over to the Fisher Gold Bug. And the reason is it just demonstrates the problem a little better. Let's crank the volume up. I've got the sensitivity cranked up pretty high on it. And what I have here is volcanic hot rock. Yeah, it's pretty well balanced out. Not quite. Let's see if we can. I don't know that I can do any better than that. But it's pretty well balanced. There, I'll show you. I'll take it off balance here. Click, click, click. That's negative. And that's positive. And that's fairly well balanced. Okay. Now, I said in the when using the Equinox that the conductive rod does cause null problems with the coil. The other thing that can happen is that with the conductive rod near the coil, a hot rock that was previously tuned out suddenly becomes very detectable. But it's not the hot rock that's actually being detected, it's the rod. And what's happening is this hot rock distorts the magnetic field as it's going by. So you've got this magnetic field going on, everything's stable, you swing this hot rock by, it momentarily distorts the field, and then the field comes out of distortion, And the act of going in and out of distortion creates eddy currents in this carbon fiber rod, and they're dynamic eddy currents. They're not static. You know, right now there's static eddy currents going on in there. It's screwed up the null on the coil, but the detector is in motion mode, so it ignores it. But when the hot rod goes by, it generates momentary dynamic eddy currents in the carbon fiber rod, and you hear it. Now, again, this is with the rod laying across the coil. You know, how big of a problem is it in reality? Well, like that, you're just not hearing anything. The reason is when the coil is normal to the rod, the detector only sees the end of the rod. It doesn't see the surface of the rod, and the surface is what's causing most of the problems. And so if you have the rod vertical like this is not a problem. As you start laying the rod further back, it can become more and more of a problem. I'm not hearing it now, but well, there it goes. So, and then you lay it down, and it's actually picking up the hot rocket several inches. So that's another potential problem with using carbon fiber rods. And again, you know, you're not going to hear this on a 4 kilohertz or a 10 kilohertz detector, maybe not even a 20. But as you get up into the super high frequencies used for gold prospecting or pulse induction, which has really fast edges, you can hear this. Minelab actually has a patent on adding shielding to solder joints inside the coil, because a solder joint can do the same thing that this was doing. You run the hot rod past, it distorts the magnetic field, it generates a eddy current in the solder joint, and it looks just like a number 2 shot or whatever. And Minelab has a patent on putting shielding around solder joints and other conductors inside the coil to prevent that particular problem. And then here we are with our conductive lower rod, again causing the same problem, and there's no way to get rid of that in this particular situation. So yes, the conductive rods can be a problem. I would not worry about it unless it's you know, really high frequency gold detectors, BLF or PI. I would probably just not worry at all about it if I'm running probably even multi-frequency mode for coin hunting and stuff. You know, you're just not likely to hear it either with this problem or with just bumping things around. So that sort of sums up what I wanted to show in this video. That you know, again, is it a problem? Well, it all depends, and that's really the final answer.